Hello and welcome to the first video of our Introduction to Data Structures and Algorithms series. In this first video, we are going to start from absolute zero. Even if you are never programmed before or never heard of data structures and algorithms, you will understand these concepts by the end of this series. We will answer these three fundamental questions. What is data? How does data become information? What are the different levels of data types, primitive, user-defined and abstract data types? By the end of this, you will see that the simple number like 42 means nothing until we organize it. And the organization is exactly what data structures provide. So let's begin. So in this title, it's mentioned Introduction to Data Structures and Algorithms, and the subtitle tells building efficient solution to solve real-world problems. Efficiency is a keyword in computing. Efficiency means two things: speed and memory usage. A solution that works but takes an hour to run is not efficient. A solution that uses 10 GB of RAM on a phone is not efficient. Data structures and algorithms are the tools that help us balance speed and memory. They are not just academic, like Google, Amazon, and every tech company uses them every second of every day. So here's our agenda for this series. Don't worry if some terms look new, we will go step by step. So what's data? From data to information, and data types, and what's a data structure, and why we need those data structures, what is an algorithm, and classify those data structures, and what are those advantages of data structures. So let's begin with what's data. Data is raw, unprocessed facts or figures or symbols. It has no meaning by itself. Let me repeat that: no meaning by itself. Looking at these examples, these are just numbers. They could be ages, scores, temperatures, or lottery numbers. You don't know. These are just letters. Is that a name, a password, a random sequence? Without context, you cannot tell. These are also just three numbers. Could be room numbers, HTTP status codes, or error IDs. Here's a thought experiment. A number written. If I give you a piece of paper with a number written on it and I say nothing else, what does it mean? It could be your age, the number of students in the class, the temperature in Celsius, or a jersey number, or an answer to a math problem you don't know. That's data, raw and meaningless. Now, why does this matter? Computers store millions of numbers and letters. Without a way to organize and interpret them, they are just piles of data. Human brains need information, data with context. That's where data structures come in. From data to information, when the data is processed, organized, and given context, it becomes information. Look at the table on the slide. The left column shows raw data: 15, 23, and 14. See the difference? The raw numbers could mean anything, but once we add the label ages of the students, now you understand. You can make decisions. For example, the average age is about 17.3. Computers store only raw data, zeros and ones. Human need information. Data structures are bridge that helps us convert data into information efficiently. Without data structures, a computer is just fast but dumb machine. With them, it becomes a smart assistant. Let me work through a concrete real-world example. The HTTP codes. These are codes your browser gets from a web browser. But these are now raw data that all have just numbers. No one knows what they mean. In here, it processed with a data structure. First, we sort them through here. They are already in order. Then we organize them and into a data structure, a table or dictionary. We add a label, HTTP status codes. We group them into categories like information, success, redirectional and client error. In step 3, now we have information. 101 switching protocols, 202 accepted, and 303 see another, 404 not found. When a web developer sees 404, they immediately know page missing. That's actionable information. Data structures transform raw, meaningless data into useful information by providing organizational context. Without this pipeline, the web could be incomprehensible. Now let's talk about data types. A data type defines two things: a domain of values, and it means what kind of data can be stored, and the operations allowed on those values. We have three levels of data. Let me explain each with care. Level 1, primitive. These come with programming languages. Examples like integer, float, decimal, char, boolean. They are one-dimensional, fixed in memory size, static, and usually local to a function. And in typical takes 4 bytes. You can add, subtract, multiply, divide and compare. That's it. The second level is user defined. You can create this by combining primitive types. Examples like arrays, structs, classes. The array of 10 integers is a user defined type. It stores multiple ints in row. You can access the fifth element. That's an operation. A struct must combine an int and char array name. They can be static or dynamic. In level 3, we can define abstract data type. This is a higher level of thinking. An abstract data type defines what operations you can do, but not how they are implemented. For example, in later sessions you will learn about stack. Abstract data type says you can push an item onto a top and pop an element off the top. That's the interface. But the stack could be implemented using an array or array. You as a user of the stack don't care about the implementation. You only care about push and pop working correctly. Similarly, a list abstract data type says you can add an item, remove an item, get an item by index, or maybe get the size. The internal implementation could be array or a linked list. Why this is important? Because it allows abstraction. You can design your solution using abstract data type first. Think about the behavior, then later choose the actual data structure what fits your performance need. This is the fundamental skill in software engineering. So in this video we have learned about what is data, and data is raw and meaningless, and information is data plus the context. Data types ranges from primitive to user defined to abstract data type. In the next step you will finally define what a data structure is, why we need them,